Today, we're going deep, right down to the atomic scale, to follow a scientific quest that is happening as we speak. It's a journey to gain perfect control over some of the most powerful new materials on the planet, a family of materials called MXenes.
So here's how we're going to break it down. First, we'll cover the basics of how you even unlock these 2D materials. Then we'll look at the difference between what you might call aggressive versus mild etching. After that, we'll get into the molten salt revolution that completely changed the game. That leads us to how scientists control the very surface of these materials, which is crucial. We'll even see how they choose the exact right recipe for the job. And finally, we'll peek into the future, a future that is truly custom-made.
Okay, so first things first. How do you get from a chunky three-dimensional material to this ultra-thin two-dimensional wonder? Well, the whole challenge is really about subtraction. You have to figure out how to remove just the right parts and nothing else.
It all starts with something called a max phase. The best way to think about it is like a book. You've got these strong pages. Those are the M and X layers, made of metal carbides or nitrides. And holding them all together is this weaker binding. That's the A layer. The entire goal is to find a way to dissolve that binding, that A layer, so you can free the individual pages. And those pages, well, those are your 2D MXenes. So the whole thing really boils down to this 3-step recipe. You start with your raw max phase powder. Then you bring in a chemical etchant. Think of it as a super precise chemical scalpel to carve out only that A layer. Once that's gone, you're left with a stack of 2D layers that are barely holding on to each other. The last step, called delamination, is just separating that stack into individual atom-thin flakes.
Right, but as you can imagine, not all chemical scalpels are made equal. The early days of making MXenes were, well, a bit of a brute force operation, and scientists pretty quickly realized they needed a tool with a little more finesse. The very first method used concentrated hydrofluoric acid, or HF. Now, this stuff is incredibly good at dissolving that A layer, but it's also unbelievably corrosive. It gets the job done, for sure, but it's kind of like using a sledgehammer to perform delicate surgery. It's powerful, but it's not exactly subtle.
So this problem led to a really key innovation, the mild method. Instead of just dumping in concentrated HF, scientists tried mixing hydrochloric acid with a salt, like lithium fluoride. What this does is it generates the hydrofluoric acid in situ, meaning it's created right there in the mixture, slowly and gently. And the difference in the result? It's night and day. The aggressive method gives you this messy accordion-like structure, while the mild method produces these beautiful, neatly stacked layers of much higher quality material.
And believe me, this isn't just about looks. That gentler process gives you a way higher quality material. By being less aggressive chemically, scientists can create much larger MXene flakes with far fewer defects on the atomic level. And that is absolutely crucial, because every single one of those tiny defects can mess with the amazing electronic and physical properties we're trying to harness in the first place.
Okay, so that mild method was a huge step forward, but the real game changer, the real revolution, was just around the corner. It required scientists to think completely outside the box, or in this case, completely outside the beaker of acid.
This led them to a really fundamental question, the one that would drive the next big breakthrough. What if they could get rid of the liquid acids entirely? Could they find a totally new chemical environment that would work just as well, but maybe give them even more control?
And the answer turned out to be a huge yes. And it came from a very hot place, molten salts. So forget the room temperature acid bath. This method involves mixing the max phase powder with a special kind of salt, a Lewis acid, like zinc chloride, and cranking the heat to over 500 degrees Celsius. At that temperature, the salt melts into a liquid and acts as the etchant, cleanly plucking out the A layer with no dangerous liquid acid in sight.
Now, this new method wasn't just a safer alternative. It unlocked a level of surgical precision that scientists had only dreamed of. Suddenly, they could control the very surface of the material, atom by atom. And as it turns out, with these materials, the surface is everything.
You see, when you etch away that middle A layer, you're leaving behind these exposed, raw metal atoms on the surface of your new 2D sheets. And those atoms are really unstable. They immediately want to grab onto whatever else is floating around in the chemical soup. The atoms they grab onto are called terminations, and these little guys are what ultimately define the MXene's final properties, from how well it conducts electricity to how it reacts with other chemicals. And this is where it gets really cool. This table just lays it all out.
When you use old-school hydrofluoric acid, you get a messy mixture of oxygen, fluorine, and other terminations. The milder acid method is a bit better, but it's still a mix. But when you use molten salts, you get incredible purity. Etch with zinc chloride, you get only chlorine atoms on the surface. Use cadmium bromide, you get only bromine. It's an unbelievable level of control.
This basically opens up a massive new toolbox for designing materials. Scientists suddenly have all these new, pure surfaces they can create. And what's even crazier is they can then swap those atoms out for other ones, like sulfur or selenium. This is really the holy grail of materials science, the ability to engineer a material's surface, atom by atom, to perfectly tailor it for a specific job. So with this whole growing toolbox of options, from harsh acids to these high-precision molten salts, how does a scientist actually know which tool to pick for the job? How do they predict if a certain recipe is going to work or if it's just going to be a big failure? The whole goal is to land your combination of materials in that sweet spot, the bottom right quadrant labeled A etched. If your max phase and agent combination falls in this zone, the physics says you're good to go. The prediction is that the agent will do its job perfectly, selectively removing that A layer while leaving everything else untouched. That's the recipe for a perfect MXene. All the other zones represent different flavors of failure. One quadrant means your etchant was too strong and dissolved the whole thing. Another means it attacked the wrong part of the crystal. And the last one means, well, nothing happened at all. So this map is just as much about avoiding those dead ends as it is about finding the path to success.
At the end of the day, it all comes back to this one simple idea. It doesn't matter if you're using acid or salt, if it's hot or cold. The absolute non-negotiable key is to achieve highly selective etching. You have to remove only what you want to remove and leave the rest perfectly intact.
So what a journey, right? We've gone from a blunt chemical hammer to a whole suite of precision scalpels. The story of how we make MXenes is a perfect window into how science works, moving from a raw discovery to incredibly refined control. What began as a single interesting material has now blossomed into an entire designable family of possibilities. And that really brings us to the final, most exciting thought. Now that scientists have the power to choose the atoms, control the defects, and design the surfaces exactly how they want them, they're no longer just discovering new materials, they're designing them from the ground up. And with that power to build MXenes atom by atom, the question isn't what can they make anymore. The real question is, what grand challenges are they going to solve next?